In this video, we are going to continue our exploration of the notion of completeness. We begin with a definition that should be very familiar to you from our study of topology on the real line. This is the definition of uniform continuity. And the definition is exactly what you would expect if someone were to tell you, please define uniform continuity for me. This is the definition that you should come up with yourself, even if you have never seen it before. So the definition is as follows: let X and Y be metric spaces. We say F from X to Y is uniformly continuous. If for each epsilon greater than 0, we can find delta greater than 0 such that dxy less than delta implies d f of x f of y is less than epsilon. If this definition looks vaguely familiar to you, well, that's because it's exactly what you would expect. What uniform continuity says is the following thing, that the continuity for checking continuity, given any choice of epsilon and given a point x, you must be able to find a delta that works in the epsilon delta definition. What uniform continuity requires us is this choice of delta does not depend on the point x in question. So you must have, whenever x and y are suitably close, then you must immediately have f of x and f of y to be suitably close as well. So the choice of delta is a function of only epsilon and is independent of the choice of point. And as you can expect, the notion of uniform continuity will behave well with respect to compactness. That is, any continuous function on a compact set will become uniformly continuous. The exact same proof will work. Once we develop the machinery for compactness, I will at that appropriate point leave it as an exercise for you to show that a continuous function on a compact set is automatically uniformly continuous. So I'm not going to bother writing down more examples of uniformly continuous functions. You have already seen several of them when we studied topology on R. Rather, what I'm going to do is I'm going to prove one important theorem that we already left as an exercise way back when we studied topology on the real numbers, but this time I'm going to give a full proof because this is going to be really important for applications. So that theorem is as follows. Theorem let X be a metric space, and let Y be a complete metric space. Let Y be a complete metric space. Let S subset of X and F from S to Y be a uniformly continuous function. So what I'm doing is I'm considering a subset S of the metric space X. I am giving it the subspace to metric. I'm treating S as a subspace of X, and I have a uniformly continuous map from S to Y. Note Y is complete. No such assumption is made on X. Okay. Now here is what the result says. Then we can extend F to a continuous map from S closure to Y. Okay. In short, any continuous map, or rather any uniformly continuous map from a metric space to a complete metric space extends in fact to the closure. Okay, so let's prove this. The proof is exactly the same idea what we have seen before, but let's write down all the details. Okay, now the essential idea that we are going to use is the fact that uniformly continuous mappings behave very well with respect to Cauchy sequences. So what we are going to do is we are going to start with the Cauchy sequence xn, and then we are going to see what happens to f of xn. So the claim is f of xn is also Cauchy. Okay. Well, why is this the case? Well, given epsilon greater than 0, there exists delta greater than 0 such that dxy is less than delta implies df of x f of y is less than epsilon. This is nothing but the definition of uniform continuity, and since f is given to be uniformly continuous, this is true. Of course, this is true for all xy, in S. Okay. So how does this help us? Well, because xn is a Cauchy sequence, there exists capital N in the natural numbers such that if n comma n are greater than capital N, then d of xn comma xm is less than delta. Okay, this is just the definition of a sequence being Cauchy applied to the case. I'm choosing delta to be the quantity the sequence must get close to eventually. So you can find a natural number n such that if n and m are greater than capital N, then d of x and xm is less than delta. This is this should be trivial at this point. This means d fxn fxm is less than epsilon. This is by uniform continuity. I'll just abbreviate it as UC. So by uniform continuity, what we have shown is that given any epsilon, we can find a capital N so large that if n comma n are greater than capital N, then d of fxn fxm is less than epsilon. Okay, so this shows that we have Cauchyness being preserved by uniformly continuous functions. Okay, now suppose x is an element of S closure and xn and yn both converge to x coming from S. So what I'm saying is, consider this set S, and suppose we are in this situation where we have two sequences from S that converge to the same point x in S closure. Then observe that if I consider this new sequence Zn, I'm not going to write down a formula for Zn, I'm going to leave that to you. But Zn is just this sequence x1, y1, x2, y2, x3, y3, and you get the big picture. It's rather trivial how to write down a precise formula for Zn. I'm going to leave it to you. This sequence Zn is also Cauchy. Okay. This is a rather easy check because both xn and yn converge to x. You can prove in a line or two that Zn must be Cauchy. Consequently, f of Zn is also Cauchy. That's what we just established a few minutes ago. But f of Zn is Cauchy and y is complete. Y is complete. So f of Zn converges to some element in y, to something. I don't care what it is. Something in y. Okay. Well, why am I saying all this? Well, that just means f of xn and f of yn converge to that same thing. Converge to the same element. Simply because these both are essentially subsequences of f of Zn. So I'm being a bit vague and imprecise here, but I trust that you are at a stage of mathematical maturity where you can make such vague statements quite precise in a matter of minutes. Okay, so what have we achieved? What we have achieved is if xn in S converges to x in S closure, then f of xn converges to an element z in Y, and the z is independent of the choice of xn converging to x. It depends only on the point x in S closure. It does not depend on the particular sequence you choose to approach this point x coming from the set S. Okay, so we can define G from S closure to Y as follows. Choose any sequence xn in S converging to x in S closure, and define, let me go to the next page, just give me a moment. Define g of x to be limit n going to infinity f of xn. So up until now, the entire discussion has been to show that this g is well defined. It does not depend on the choice of sequence xn we choose. Furthermore, if x is in S, we can consider the constant sequence x, rather x, repeat. So I'm just calling it the constant sequence x to show that, or rather to see that g of x equal to f of x. Okay, what have we achieved? Well, what we have achieved is the following. Given this function f from S to Y, we have found out an extension g from S closure to Y. Now, what remains to be seen is why is this function uniformly continuous? Sorry, why is this function continuous? In fact, we are going to show that it is uniformly continuous, but the theorem just claimed that g is continuous. So we will again check the epsilon delta definition. So fix epsilon greater than 0 and choose delta greater than 0 coming from uniform continuity of f. Okay, so the rest of the argument is in fact going to establish that g is uniformly continuous, not just continuous. So the choice of delta comes from the uniform continuity of the function f. So let x comma y be elements of S closure. Okay, and such that dxy is less than delta by 3. I'm going to show that d f of x f of y is less than epsilon. This is a standard argument that should be familiar to you by now. Anyway, let's run through the argument quickly once more. Let xn in S comma yn in S be such that xn converges to x, yn converges to y. Okay, you will understand in a moment why we chose this particular delta by 3 and not delta or delta by 2. Why delta by 3 is crucial. Okay, so now I'm going to start a new page. Choose n so large that first of all d of xn comma x, d of yn comma y are both less than delta by 3. Okay, remember d of xy was less than delta by 3. So if x is here, y is here, so let me not draw a primitive ball. What I do is I choose x and y close to each other. Okay, the distance between x and y is at the max delta by 3. Now what I'm saying is choose delta by 3. I mean, these are very badly drawn figures, but it will give you an idea of what's going on. So this, if this is x, this is y, I'm saying choose xn coming from here, yn coming from here. Okay, that's part 1. Second step is d fxn comma fx d fyn comma f of y. Sorry, there's a slight mistake here. F of y doesn't make sense. This is g of x and this is g of y, because x and y are coming from S closure. Let me just check whether I have not made a mistake here. Yes, x and y are coming from S closure. So you cannot really say f of x and f of y. That doesn't make sense. And anyway, that is irrelevant to our purpose. Our interest is solely in showing that the distance between g of x and g of y is less than epsilon. So what you do is you choose n so large that first of all d of xn comma x, d of yn comma y are both less than delta by 3. And d of fx and gx and d of fy and gy, both of these should also be less than epsilon. Both quantities should be less than epsilon. Now we have ensured by our choices that d of fx fy is actually going to be less than 3 epsilon. Why is that? Well, d of f of x f of y is going to be less than or equal to d of f of x f of xn plus d of f of xn f of yn plus d of f of y f of yn. Okay. Now these two quantities, d of f of x f of xn and d of f of y f of yn, are both less than epsilon just by this. However, d of f of xn f of yn is also less than epsilon simply because d of xn yn is less than d of xn x plus d of yn y plus d of xy, which is less than delta. So now you should understand why we chose that particular choice delta by 3 at this point. At this point, why we chose delta by 3 and not anything else. So that's it. This completes the proof. D of f of x f of y is less than 3 epsilon. Okay. Therefore, we have that. Okay, I made a slight error here. Sorry about this. This is g of x, g of y, and again I must change certain f's to g's to be correct. So usually what happens is the extension is also denoted by the same letter f, but here I have used g, so I must use g. Okay, note that at these places also I could have replaced f by g. It really doesn't matter because on the set S, f and g agree. Okay, so this concludes the proof that g is continuous, in fact uniformly continuous. So let me end this video by some remarks about the property of completeness with respect to topology. Okay, completeness is not a topological property. Okay, just like what do I mean? Just like boundedness is also not a topological property. I'm not going to rigorously define what a topological property is. That is going to be left for the future when you do a course on topology sometime. A topological property, loosely speaking, is a property on a metric space that can be characterized completely using open sets. This is just vague, okay? I'm not being 100% precise. We have already seen that boundedness cannot be characterized completely just using open sets. In fact, you can find a metric space with two different metrics, or rather a set with two different metrics that are equivalent in the sense that the open sets are same, but in one of them X is bounded, in the other X is not. We have already seen an example of this in an earlier video when we discussed equivalent metric spaces. So being bounded is not a topological property, right? It's not a topological property. I was right. Being bounded is not a topological property. What about completeness? It looks like completeness will also not be a topological property because the definition of completeness uses Cauchy sequences and all that, and not just open sets. However, you will see in a future video that compactness is also defined in terms of sequences. In fact, I can briefly give the definition. A metric space is said to be compact if every sequence has a convergent subsequence. Exact same definition that we saw for for the real numbers. So compactness is also defined in terms of sequences, but compactness turns out to be a topological property. So just because something is defined in terms of sequences does not mean that it is impossible for that to be a topological property. Okay. It just so happens that you can characterize completeness entirely in terms of open sets. Same remarks apply for closed sets. Closedness is also defined using sequences. However, you can characterize closedness completely by open sets. Okay. But completeness is not a topological property. To see that, what you do is consider this set 1 by n, which is a subset of R. Okay. So of course n coming from the natural numbers. Here you can put the usual metric, that is the subspace metric. Okay. Now any subset of 1 by n will be open. This is something that will be utterly easy to see. Okay. So what does this tell us? Well, note that 1 by n under discrete metric gives the same topology. That is, if you put the discrete metric on the set 1 by n, you get exactly the same open sets as when you put the Euclidean absolute value metric on 1 by n. But in an earlier exercise, you would have explored and you would have realized that any set with discrete metric is actually complete. If you have not explored that, please do so now. It's important. Any metric space that is coming from the discrete metric is automatically complete. So when you put the discrete metric on 1 by n, it's going to be complete. Obviously, when you put the usual metric, it's not complete because 0 is not there as an element of 1 by n, and 1 by n converges to 0. This shows that you can have two different metrics on the same set which give rise to exactly the same topologies, but one of the metric spaces is complete, the other is not. This concludes this video on completeness continued, and you're watching this course on real analysis.